Nuclear stability. In this video, we will learn the rules for nuclear stability and use them to determine which type of decay an isotope is likely to undergo. Stability is determined by several rules along with the proton to neutron ratio. Let's take the proton to neutron ratio first. As atomic mass increases, the ratio of neutrons to protons must also increase. For light elements, it is generally a 1-to-1 ratio and increases in the number of neutrons as the atoms get heavier. These increased number of neutrons will give a larger binding energy, which, as we learned in the last video, gives us increased stability. This is also because they help to counteract the repulsions of the higher number of protons. Radioactive decay will occur in a way that gets the atom closer to the band of stability that you see in the chart above. This is the dark black band running through the isotopes. We'll zoom in a minute and look at what this means for the type of radioactive decay that occurs. There also happens to be several rules that the universe seems to have set up. You won't have to memorize these, but it is worth noting them. For instance, we have magic numbers. 2, 8, 20, 28, 50, 82, and 126. Protons or neutrons happen to be more stable. Nuclei with an even number of protons or neutrons happen to be more stable than the ones with odd numbers of protons and neutrons. All elements with Z equals 83 plus are radioactive, and all isotopes of Tc and Pm are radioactive. With those rules aside, let's also look at in more detail at the decay that happens in order to reach the band of stability of the ratio of neutrons to protons. Here we have a very zoomed in version of the graph on the last slide. If species are above the stability band, as we have right here, they have too many neutrons per proton. They will undergo a beta minus emission, which effectively changes a neutron into a proton from a numbers term, lowering the ratio. For atoms that are below the stability band, such as we have here and here, there are several ways which they can undergo decay to reach a stable nuclei. I've shown two here. In one case, emitting a positron, which will effectively change a proton into a neutron, decreasing the ratio of protons to neutrons. And then also just emission of a proton, which of course will also lower the ratio of protons to neutrons. Since we won't always have a full chart to zoom in on, and charts are typically quite difficult to read precisely, generally the stable nuclei are reported either by ideal mass to proton ratios, ideal neutron to proton ratios, or by simply giving you the isotopes of a given proton number that are stable. Let's do two examples. Predict whether each nuclei will undergo beta decay or positron emission. Here I've chosen to give you the stable nuclei of magnesium, so we know that all the decay processes are going to happen in a way that gets us closer to this ratio of protons to neutrons. Let's take magnesium 28. Magnesium 28 is higher than the ideal masses, and therefore it is too heavy, or in other words, there are too many neutrons. So we need to lower the number of neutrons. To do this, we can undergo beta minus decay, which emits a negative charge, thereby lowering the number of neutrons and increasing the number of protons. Let's do magnesium 22 now. Magnesium 22 is the opposite situation. It's too light compared to the stable isotopes of magnesium, which means that it has a low neutron ratio. So what we'll want to do for this is increase the neutrons, decreasing the protons. To do this, we need to use positron decay, since a positive charge is emitted, making a proton into a neutron. Now let's review. For a given atom, there is an ideal ratio of protons to neutrons, as well as several rules that the universe follows in order to show us for increased stability. Nuclei will decay in a way that brings them closer to the ideal ratio and will also attempt to follow the rules that we laid out. Notice I can't exactly test you on those rules when it comes to guessing decay. Neutron-rich nuclei tend to undergo beta decay, while neutron-poor nuclei tend to undergo positron decay.